set, Andrew?
Yeah, looks good, I think.
Okay, good morning everyone. Welcome to today's seminar. So today we have Andrew Cumming from McGill. Andrew works on stellar astrophysics, compact objects of all descriptions, neutron stars, white dwarfs, hot Jupiters, normal Jupiters. And today he's going to tell us about anti-diffusive dynamics, which is just what we need.
Right, at least I'll try. Yeah, I have a colleague who says that I will work on anything round. So anyway, which we'll get to. So we've been working on a couple of problems in astrophysics recently that involve anti-diffusive dynamics. So I thought it might be interesting to talk about them here. And I'm hoping there's some overlap with other areas. As you'll see, we've only really just begun working on these topics in astrophysics, and we don't have a really good understanding of how things like layering works inside Jupiter, for example, and you know, how we can model that over the billions of years of Jupiter's lifetime. So I'm really hoping to try to make some connections with other areas and perhaps, you know, get some feedback. And I haven't tried to put too much into this talk. Famous last words maybe, but please do interrupt. You know, I'm happy to be interrupted, and we can have a discussion as we go along. Before I begin, I just want to highlight that a lot of the numerical work I'll show was done by Rafael Fuentes, who was a PhD student with me in Montreal, and now he's a postdoc in Boulder. And at the moment, I have a PhD student, Matthias Castro-Tapia, who's working on the white dwarf aspects, which I'll show towards the end. Okay, so these two problems I'm going to talk about, one of them is mixing composition in Jupiter, and the other one is crystallization in white dwarfs. They both have what they have in common is that they both involve composition gradients interacting with convection. And that interaction creates some kind of anti-diffusive dynamic, as I'll show you. And the other aspect is that they're problems that are driven by boundary fluxes. And those boundary fluxes, as I mentioned, we want to evolve these objects over gigayears in time. And over that time scale, these boundaries move, and the boundary fluxes change with time. So there's a secular evolution aspect of these problems as well. And in astrophysics, because we're trying to model observations, we want to evolve things over very long timescales. We're typically doing spherically symmetric one-dimensional models in which all the fluid processes are parameterized, or we have prescriptions. You know, so the classic example would be if I want to model convection in a star, I use mixing lamp theory. And I'll show you some mixing lamp theory later. But what we're trying to do, the strategy we're kind of taking is we can't simulate a full star for billions of years, but we can do localized, idealized simulations to try to learn something about the physics aspects and how the physics is working. So an example would be layer formation. I'm going to talk a little bit about layer formation. So we'll do some simulations to try to understand some aspect of that we can then feed back into the longer-term evolutionary model, which is spherically symmetric and has the prescriptions. Right? So that's the kind of strategy that we're taking. And the two problems I want to talk about, one, I'll spend most of the time on Jupiter, and then at the end, depending on how much time I have, we'll talk about white dwarfs. So in Jupiter, we're interested in how convection interacts with heavy elements inside Jupiter. And I've drawn here a picture of Jupiter which has a heavy element core in the center, and then an envelope which is convective, a gas envelope which is convective. And this is kind of a traditional picture of Jupiter based on the idea that the way gas giant planets form is that you build up a rocky core, rock ice core in the protoplanetary disk, and when that core gets to about 10 Earth masses, so we're quite far out, you know, Jupiter's location quite far out in the disk, there's a lot of solid material there, condensed material, ice and rock, that you can gather together. If you can get to 10 Earth masses, then you trigger a runaway accretion process where very quickly you can accrete a lot of gas. And to make Jupiter, we need to accrete about 300 Earth masses of gas. So you have this 10 Earth mass core, and you add on, which is rock and ice, and then you add onto it 300 Earth masses of hydrogen and helium. So the traditional picture of Jupiter would be, I have a rocky core, 10 Earth masses in the center, and then on top of that, there's this big massive envelope of hydrogen and helium. And when I say it's driven by boundary fluxes, what's happening here is that Jupiter's cooling from the surface, so you're cooling this gas envelope. The gas envelope becomes convective, we want to study how does that convection interact with the composition gradient, because we know deep down inside Jupiter there's a lot of heavy elements. How does the convection interact with that? And the traditional picture is this very clean separation between the core and the envelope, and that's become more complicated in recent years, and that's what I want to show you. And there's an opportunity here for layering. If you think about this, I'm creating an unstable thermal gradient, but I have a stabilizing composition gradient. And so in that situation, you could get layered convection. So that's what I want to talk about in the Jupiter case. How a layer is forming, what does layered convection do inside Jupiter in terms of evolution. And then in white dwarfs, so white dwarf is the compact remnant from a star like the sun, right? The last nuclear burning stage in the sun is going to be helium burning. Helium burning makes carbon, oxygen, and then you throw away, you eject the rest of the gas envelope, you're left with this core of carbon, oxygen. It's about the size of the Earth, but the mass of the sun, right? That's the white dwarf. So it's the mass of the sun compressed in the size of the Earth. It's a degenerate object. Eventually, they've lost their envelope. They're just sitting there. This Earth-sized object is cooling down. So the evolution of white dwarfs over billions of years is that they just cool down. And if you cool the white dwarf enough, the plasma inside will form a solid. It's a fully ionized plasma, so the electrons are completely stripped from the nuclei. But at low enough temperatures, about 1,000,000 degrees, it's so dense in there that at 1,000,000 degrees, the nuclei feel the Coulomb interaction with each other, and they drop into a lattice. And you form a material that has a shear modulus. Just like this remote, has a shear modulus. So it really has the properties of a solid. So you've made a plasma which has properties of a solid. And just like in the Earth's core, for example, or in metallurgy, if you solidify something which is a mixture of different elements, then the composition in the solid is not usually the same as the composition left behind in the liquid. Depending on the phase diagram, there'll be a difference. And in the white dwarf case, what happens is that we believe is that the carbon-oxygen mixture, when it solidifies, it preferentially keeps oxygen, and the carbon gets pushed out, a little excess of carbon gets pushed out into the liquid. So there's a buoyancy source there. At this interface, there's a growing solid core. At the interface, you're injecting light elements. You can drive compositionally driven convection. And the reason I wanted to just talk about it a little bit is that I think it's a really interesting regime of convection that I don't think happens anywhere else, which is that I'm driving convection with composition, but I'm doing it in a situation where I'm very thermally stable. There's no way it wants to thermally convect. The conductivity is so high that it's very thermally stable. So that means that the heat transport in the system is up the temperature gradient. So I'm driving the composition, using composition to drive convection, I'm transporting heat in rather than out. So that has some interesting consequences, and we're trying to model this system. Okay.
This crystallization, how good are the experimental data? I mean, you can tell the crystal's height.
We don't have experimental data, but we have Monte Carlo and molecular dynamics simulations. It's a screened Coulomb interaction, so it's fairly straightforward to model. And the crystallization temperature is well understood as a function of density. Forms even the lattice type, I think, is pretty well understood. And we have some understanding of the phase diagram. So I don't have it in this talk, but I could show you phase diagrams and so on. So it's because the interaction is fairly straightforward. I would say it's reasonably well understood, the solidification. But we have no experimental tests. So one of the interests in this is, for example, I'll show you some data where we've inferred the latent heat. So the latent heat is something just predicted theoretically, but you can use white dwarfs to try to measure the latent heat value, for example. Okay, so let me talk about Jupiter to begin with then. And both of these problems are observationally motivated. So I just want to talk a little bit about the observational motivation. And I don't have a lot here, so please ask questions. But what's changed really, I mentioned that there's this traditional picture of Jupiter, rocky core, gas envelope. But what's changed in the last 5-6 years is that there's now significant evidence that it's more complicated than that. And not a surprise, perhaps, but the first thing is that Juno is a mission that is currently orbiting Jupiter. It's been there for about 5 or 6 years now. It's orbiting Jupiter, and it's measured very precisely the gravitational moments of Jupiter. So we now have an updated set of gravitational moments for Jupiter. And from that, you can infer the density profile inside Jupiter. So you measure the density as a function of radius inside the planet. And you can imagine, if you know what the equation of state is, if it was an ideal gas, for example, if you know the density, you can infer something about the composition. Is it heavy or light? You can get the composition profile. Now, in Jupiter, it's more complicated because we don't have ideal gas. It's a more complicated equation of state. The hydrogen molecules are crammed so close together in the center that they form a metal, you ionize the molecules and you form a hydrogen metal. So inside Jupiter, you go from this sort of indicated in this diagram here. You have metallic hydrogen in the inside, molecular hydrogen on the outside. There's a transition there. This equation of state, there are some experimental constraints, but it's not experimentally measured all the way along the adiabat here. There's significant uncertainty in this equation of state. So when you take the density profile and you try to back out the composition profile, there are uncertainties there connected with the equation of state. But in all the models that people have made, it seems that this condensed core structure that I talked about really doesn't fit the density profile that you see. Instead, what you need is something that's much more extended. So this is a cartoon sort of showing this. So you have the central core here, but there's an extended region where the heavy elements are extending out into this convective envelope. And this extension could be as much as 50%, even 60% of the radius. So it's a very significant extension. And this is sometimes called a fuzzy core or a diffuse core. So it's not a compact core, it's more of a diffuse core. And interestingly, there's the same conclusion for Saturn. So first of all, from gravitational moments again, but I think most interesting recently has been this detection of density waves in Saturn's rings, which are in resonance with they're excited. So the density wave isn't in Saturn's rings, but it's excited by a resonance with internal waves in Saturn. And so by modeling the frequencies of the internal waves in Saturn, you can make a match here with the density waves in the rings. And so the inference is that there are internal waves in Saturn. There are stable regions inside Saturn that support these internal waves. And in particular, Mankiewicz and Fuller, this paper 2021, they modeled, again, the composition profile, and they found that you need one of these sort of fuzzy extended cores, or at least, I think the way to say it is that a fuzzy core is able to match the frequency data, from the ring seismology. So it seems like both of the gas giants seem to have these extended cores.
Are the IWs excited?
That's a good question, yeah. Probably, that's a good question. Probably from the convection.
Okay.
Yeah, but actually, I'm not 100% sure about that. That's interesting to look into. I'm not sure. So my interest in this came from, I was thinking about planet formation. And so obviously, if we have Jupiter today or Saturn today and has this extended composition profile, one interesting thing about that is that it can tell you something about when Jupiter formed or how Jupiter formed, right? So when Jupiter formed, you have to make it in such a way that the composition profile, if you evolve it to today, has to be out to 50, 60% of the radius. So you can imagine that could be quite a constraint on the formation model. It's not like I just make a 10 Earth mass core, I suddenly accrete a metal-free gas onto it. That's not going to work unless I can dredge up the core into the envelope, for example. So we get to this issue of convection. How does convection interact with the heavy elements inside Jupiter? Okay, so that's what we tried to do. So we used some 1D models, these spherically symmetric models I'm talking about, to try to address exactly this question. Can I go from formation to a picture like this for Jupiter today? Okay, and let me show you what that looks like. And there's a puzzle here. We can't seem to get it to work. So this was work with Simon Muller, who's a student with Ravi Taled. Now he's a researcher in Zurich. And these panels here show you against a mass coordinate. They show you the heavy element fractions. So these are heavy element profiles inside Jupiter. And the dotted line is what we have at formation. So there are four different models here. And what we've done is just to vary the rate at which I accrete solids or gas. When I build up the planet, I just vary the way I do that to get different amounts of, different profiles for the heavy elements. And the dotted lines show you the profile at formation. So this one on the top, it has a very compact core of heavy elements. I put the heavy elements in the center. This green one, for example, is much more extended heavy element profile. And then we tried to play this game of, let's make Jupiter this way, evolve it for 5 gigayears till today, and see what it looks like. And you do this in 1D. So I'm using mixing length theory for convection. I'll talk more about that in a minute. We're using the Ledoux criterion for whether convection is happening. We just evolve it. And the solid line shows you what you get for Jupiter today, okay, if you do this. And I think you'll see, well, first of all, do you see some steps here emerging? So in the 1D code, there's a staircase emerging. But also the other thing is that we don't really get anything that looks like the extended core. This lower panel is meant to show you inferences from the data, what the extended core looks like. It should go out to 50 to 60% of the radius. It's fairly shallow like this, but it drops off on the outside. But what we find is that either if you put in a very centrally concentrated heavy element distribution, it survives, right? So the dotted line and the solid line are basically the same, but it just breaks into a staircase, doesn't mix. Or if you put in something more shallow, what happens is it just basically mixes. So the entire outer, at least the outer part of the mass here, is completely homogeneous at the end. We don't really get anything that's in the middle. Right? So if the initial state is very steep, very concentrated in the center, it just survives. It survives by breaking into a staircase, or it just mixes the whole thing, and you get completely mixed. So at the moment, the situation is in these 1D models for Jupiter, we can't make something that looks like the Juno data. So there's a puzzle here. We want to understand how this mixing really happens. Are we modeling it correctly in 1D? Probably not, right? What's the deal with these layers here that we're forming? Okay, so that started off a whole investigation into layering, and that's what I want to tell you about. Okay, so tell me if there are any questions about these models. I mean, I'm just kind of throwing these models at you, but I'm going to go into a little bit more detail now about what's causing this layering in 1D. Okay, so we wanted to understand what's causing this layering in 1D. And actually, I should say that this kind of layering here is seen throughout stellar evolution. If you look at calculations of evolution of stars, main sequence stars, massive stars, the convection zone size often changes during the evolution. And whenever the convection zone size changes, if you have composition gradients, you tend to form staircases in the code like this. They're very, very common. So I tried to make a very minimal model. I'm just going to show you what's the minimal model you could make to reproduce this kind of behavior. So let's solve just these equations. So I'm going to just do a Cartesian grid, very simplified model. I just want to try to get at this behavior. So I just have conservation of heat equation here, conservation of energy. So the temperature is evolving because of fluxes, and the composition is evolving because of composition fluxes. And I just write down these equations on a Cartesian grid, and I'm going to solve them. And for the fluxes, what I'm going to do is, here's the heat flux. I'm going to have a component of the heat flux, which is a conductivity times the gradient, temperature gradient. So these nablas here, these del's here are the temperature gradient or the composition gradient, written in kind of astrophysics language. Is a detail we tend to put the sign wrong. So positive, we choose the sign of the gradient so that it's proportional to the flux. Anyway, but you can see here that we just have thermal conduction here, a conductivity times the gradient gives me the heat flux. Or if the Ledoux criterion is satisfied, so if I become unstable to convection, then I'm going to add in a heat flux due to convection. And for the composition flux, we'll just ignore diffusion. Let's just ignore diffusion. It turns out you can put it in, but it's not so important. I'm going to add composition transport whenever I have convection as well. So if the Ledoux criterion is not satisfied, there's no convection, I'm stable, I just have thermal conduction. Once I become unstable, the composition gradient drives me unstable, for example, or the heat gradient, the thermal gradient drives me unstable. I'm going to add in a big contribution to the flux from convection and a big contribution to the composition flux from convection. Okay, and so here's an example. I'm going to show you two examples. So temperature, composition, and the gradients here at the bottom. So I'm going to start off with an isothermal box, and I'm just going to take the temperature on the outside. I'm going to pull it down in time. So I'm just going to cool the upper boundary with time. I'm going to drive a thermal wave into the domain. Here's my initial composition. I put in some gradient. And then the orange lines down here are the composition gradient, and the blue is the thermal gradient. So when the blue is below the orange here, that's stable to convection. When the blue goes above the orange, it means that I'm driving convection. Okay, so what do you think is going to happen? I'm going to kick this off, and I'm going to start cooling. I'm going to take this grid cell. I'm just going to move it down in temperature and cool it. Oh, okay, that was really fast. What do you see? But you see the end state, right? So I basically there's a temperature gradient here, which is transporting heat flux out, because I'm cooling on the outside. So I'm just cooling down the box over time. I have some gradient because I have a flux. And then, see, it's totally mixed. So the composition gradient has gone flat. And if I do that more slowly, maybe we can kind of go through. You see what's happening is that there's a convection zone here which is penetrating inwards. In the convection zone, I just mix everything. And this is the original, I just eat up the original composition gradient until everything's fully mixed. And at this boundary, you see that in the boundary layer here, there's a stable boundary where I stabilize with the composition gradient, I stabilize everything. But over time, the outer part is just cooling down. The outer part here is just cooling down over time. So this composition, the temperature jump here over time is just growing and growing. Eventually, I've got such a temperature jump, it becomes unstable, and I mix the next cell, and in this way, convection just propagates inwards. Now this one didn't have, I put k equals 0 here, so I didn't turn on thermal conductivity, so there's no thermal conductivity here. What I'm going to do on the right-hand side, I'm now going to turn on thermal conductivity. So even with no convection, I can transport heat. Now what do you think happens? We get a nice set of layers forming. And notice what happens here, if I run it again. You form a series of layers. So the composition profile stabilizes with a bunch of layers here. But notice that the temperature profile just keeps cooling down. Once the composition profile has formed a staircase, the whole temperature profile just keeps cooling down. Right, it's cooling down. And the composition profile is not changing. So this is the idea that I've taken this initial composition profile, I've just broken into a series of steps. It's going to be constant in time thereafter. It's now going to be long-lived, and I just cool down the object with a fixed composition profile. And what's happening is that at these interfaces here, because I've turned on thermal conduction at these interfaces, I'm trying to grow a thermal contrast at the interface by cooling down the outer boundary, but conduction across the interface just keeps that delta T fixed. So that jump never grows large enough to become unstable. It just cools down. So these composition jumps, they never mix. They just get fixed. So that's what's happening in these stellar evolution codes. You just put in the composition gradient, it breaks into a staircase, and it's just fixed over time. It doesn't evolve anymore. It doesn't mix. So I happened to be visiting Newcastle when I did this. It's some years ago now, and I proudly showed it to Toby Wood. I remember proudly showing it to Toby Wood. And Toby instantly said to me, what about resolution dependence? Because I don't know if you see here, but there's never a grid point in between. I just have one grid point on one side and one grid on the other. Right? So the thickness of these interfaces is just my grid spacing in these kind of models. So what happens is that if I double the resolution, I just get twice as many layers. And in the limit where I go to very high resolution, what happens is that I just break this composition profile into many layers. And it doesn't really evolve. It completely depends on composition. So this goes back to the idea in layering. For example, Baumfuth et al., right? Or David, your work with Paul Prusina, looking at ultraviolet catastrophe for example, in the gamma instability. So if I have some composition that's going to break in, composition profile is going to break into layers, I need to put in something to regularize the thickness of the interfaces. And if you don't do that, then you form the layers want to become infinitely thin. There's nothing stopping stopping this interface just from becoming infinitely thin. That's, I think we're seeing the same problem here, but in a different situation. It's not that I'm setting up gradients and I'm allowing them to become doubly diffusive unstable. Instead, I'm driving the system from the boundary, and I'm driving the temperature gradient unstable, and layers sort of form dynamically. But you see the same issue here, that they want to become infinitely thin. We need some piece of physics in there that goes beyond. I can't just describe the system like this. I need something. I can't just have diffusive flux like this. I need to put in something more. So for example, yeah, question, yeah.
Does the same feature carry over to your stellar evolution code?
Yeah, it's interesting. So in the stellar evolution code, I think that's exactly what's happening in the stellar evolution code. And actually, Vazan et al. Previously in the Jupiter context had described it exactly the way I described it. That was stabilizing things because of thermal conduction. But the tricky part about stellar evolution is that usually you have an adaptive grid. So it's continuous. The code is trying to adapt the grid continuously to put more grid points in the high gradient regions. But it's not tuned to this problem, so it doesn't know about this problem. So it's not. It's trying to. So what happens when you run it is that the grid is continuously changing for other reasons inside the code. So the staircase is just continuously evolving. But it's the same underlying physics, I believe. Yeah, it's just that they put in adaptive time step, grid spacing. I'm not sure if that answers the question.
Oh, you did. Yeah. I seem to remember that in stellar evolution, people will put some extra things into the code to try and stop maybe problems like this happening.
Yeah, so that there's a long history of putting in convective boundary mixing in some way, or overshoot in some way, and I'll come back to that. I'll come back to that later. But it doesn't seem to stop this. It's not to really treat this layering behavior. It's more to treat what happens when I have a convection zone next to a stable region, and I want to understand the transport across that boundary. But those prescriptions, for example, they're often diffusive, and so that doesn't stop this behavior. But I'll come back to that later. So I think where we've got to is that I think there's an interesting set of interesting problem here to understand in stellar evolution codes. How can we stabilize these layers and resolve them? But, yeah.
What do you do about the transport coefficients in the story? Speaking of Baumforth and company, I mean that's of course the crux of the issue there, and the actual use of multiple mixing lengths and all of that.
Right.
So I mean, how is this handled here?
Yeah. So typically in the convective region, you choose a mixing length. There's a straightforward mixing length theory with a mixing length. There's some fraction of the pressure scale height, and then there's a prefactor which I'm not using in a very simplified model here, but there's a prefactor which has all of the local stellar conditions in it. Okay. And then for the thermal conduction, there's a thermal conductivity that you calculate from microphysics that depends on temperature and density, and it's well mapped, kind of well mapped out. And you feed those in.
And what about the composition?
But there's no sort of dependence of mixing length on turbulent energy density or something. There's nothing like that happening.
So that this community hasn't tried that kind of mixing model.
There are attempts, but not specifically in this context of layering. Yeah. So I just wanted to mention this idea here from Timon Radko. So this 2005 paper, Radko evolved just fixed gradients and formed a staircase with a 1D model like this, and noted that if you want to resolve these interfaces, you need to add some kind of higher order term into the equation. So it's what I would call a hyperdiffusivity, right? So you add a fourth order derivative. Adding a second order derivative does not do it. You need to add a fourth order derivative. But if you do that, you add, in the dispersion relation, it's like adding a higher order term dispersion relation, you cut off the ultraviolet catastrophe. So one way to think about that is that there's sort of a non-local transport at the boundary, which is somehow setting the width. So for example, I can run my simple model. I don't know if I have an example, but I could just run it. Here's an example where you resolve the boundaries. For example, putting in a fourth order derivative. But the fourth order derivative transports material out. So quickly you mix everything actually in this as soon as you put this in, depending on the value. So this could be a way forward. But it just gives you a coefficient that sets the coefficient sets the thickness of the layers in a sense, and it also determines how quickly you're transporting composition out. So this would require, some calibration to numerical simulations, for example, to try to understand exactly what to put in here. But this would be one sort of option. The Barnforth 1998 kind of idea is let's add another equation, a time-dependent equation, for example, for the turbulent kinetic energy density, and watch that grow, and then make the diffusivity depend on that, and then by putting in a time-dependent aspect to these equations, you can get a resolved step. So there are different ways to do this, and I think we haven't really figured out in this context exactly what to do. So that's one reason I'm presenting this, and that's one of the questions that we have right now. What exactly would be the good thing to do? Okay, so what did we do after this? After we kind of realized we said, okay, let's try to do some numerical simulations to try to understand a bit better what's going on here in these kind of models. There is an analogous set of experiments, actually, which remind you of what's happening in Jupiter, which are these experiments were going back to Turner Stommel 1964. And what they did here is they took a stratified tank of salty water and heated from below. So we're cooling from the top. We're growing convection by cooling from the top. But here you're heating from below. And you see here a convection zone develops eating into the salt gradient over time. The convection zone grows over time. And in this experiment, they saw secondary layers develop ahead of the convection zone. So the main convection zone is growing in, and ahead of the main convection zone, you develop these secondary layers. It looks a lot like what we're getting in these 1D models. So what we did is set up a Boussinesq simulation of exactly this, but we're going to flip it, and we're going to put in a stable salt gradient, cool it from the top. Okay, so this was work done by Rafael Fuentes. We use the Daedalus code. We're doing it's 2D. And also, those experiments were salty water, so Prandtl number is 7. In the planetary context, we want to go to low Prandtl number. So one of the goals of this was to try to maybe reproduce the experimental behavior, but also to go to low Prandtl number and look at what differences there might be when you go to Prandtl number less than 1 compared to Prandtl number larger than 1. Okay, so I think this might be a movie. Let me see. So yeah. So here's a movie of one example of a run. So we're cooling from the top, you form a convection, and convection is penetrating in here over time. This is the temperature profile on the left, and this is the composition profile on the right. So you see that where it's convective, you basically fully mix the composition, and this interface is eating its way in to the box. And if you let this run for long enough, the whole thing mixes. So if I fast forward through here, I don't know how long the movie goes. Okay, it doesn't go all the way to the end, but if we ran this for long enough that the convection zone penetrates and it mixes the whole box eventually. And indeed, this is the question we want to ask, actually, right? Because in the 1D models, what happened was you make a staircase and you fix the staircase of composition, and then you just keep cooling down with a fixed staircase. So is that what happens, or does it fully mix? That was one of the questions we wanted to look at. Okay, so I'm just going to talk a little bit about the different aspects of this simulation. So one thing that we looked at was how quickly is the outer convection zone moving in? And it turns out this is important for layer formation. So I'll just go through this in a little bit of detail here. So there's an argument from Turner that gives a square root of time scaling for the thickness of this convection zone. So as the convection zone penetrates in, how does this thickness depend on time? It actually has a diffusive scaling, t to the 1/2. It has nothing to do with diffusion. It's coming about, you just conserve energy and salt. And when you conserve energy and salt, but when you conserve energy, you have a delta T. When you conserve salt, you have a delta S. And so you also need to put in some information about the ratio of delta S to delta T at that boundary. And Turner originally took this ratio to be 1. So that's equivalent to saying, like in the stellar evolution code, at the boundary, I'm just going to become Ledoux unstable. And when I become Ledoux unstable, that's when I mix to the next cell. But Fernando proposed that instead a better value to take would be 3. And this is thinking about the idea of entrainment. So the reason the convection zone is going in is not because it's got cold enough to mix the next zone, but it's because there's an active entrainment process at the boundary that's bringing material across the boundary. For example, shear instabilities at the boundary can mix in heavy elements from below, and that reduces the buoyancy enough to allow the convection zone to propagate. And if you just do an energy conservation type argument, you can show that the value you get is a 3 here. So whatever value you take, when you put this in, because delta S goes like h and delta t goes like delta s, you get an h squared here. You get a square root scaling with time.
There's no diffusion aspects in any of this at the moment.
Yeah, we're assuming here that the diffusivity is small, which is a good approximation for the salt water. You mean chemical diffusion?
Well, there's no diffusion of any sort in this argument at the minute.
That's right. That's right. So what we did is to extend this argument, and so we wrote down the following set of equations here. And I think this aspect of diffusion, what we do here is we say, so we're going to write down an energy conservation equation, which you see these two terms here, they echo this kind of energy conservation. But we're going to write down this energy conservation in here for the temperature. And we're going to add in the fact that there's some heat flux across the interface. So the interface is bringing in heat from below. So that's where I would say thermal diffusion enters into this picture. So there is thermal diffusion across the interface into the convection zone from below, as well as leaving from above. And then the other equation we wrote down was the entrainment equation. So this goes back to these, sorry to keep flipping, back to these ideas from Fernando. So as well as energy conservation, you have an entrainment equation where you say that the rate at which the convection zone is expanding is set by the fraction of the kinetic energy that you're using to entrain material. So you just calculate the kinetic energy density at the base of the convection zone and take some fraction of that and use that to lift material across the boundary, to do the work, to mix the composition. And these parameters, epsilon and gamma, this entrainment parameter and this heat flux parameter, we can measure separately in the simulation. And it turns out these equations also have a square root of time solution. Okay, and from that you get an effective R, which is given in terms of these two parameters. So we can measure these parameters from in the simulation. We can put them into here, get the R, get the scaling, and then we can make a prediction. And that seems to match fairly well, yes. Yeah.
What's your boundary condition?
Oh, boundary condition is a constant heat flux at the surface, leaving the box, and then free slip for the fluid.
Do you think the boundary condition may impact on the...
Do you mean the velocity boundary condition?
Yeah.
Or the thing that we're very sensitive to is the kinetic energy density at the interface. So if, for example, if you change free slip to no slip, for example, at the top, then you might change, to the extent at which you change the kinetic energy density at the base of the convection zone, then that would cause some difference.
Have the boundary condition is impacted by the external environment.
Yeah, so I don't think so. I think if the convection zone is deep enough, then unless you're significantly changing the convective velocity, then I don't think it would change the entrainment rate too much. But we didn't do experiments with another velocity boundary condition. So.
I mean, just a remark, all of what you just said sounds like an excellent advertisement for adding some sort of dynamical evolution, right, in the mixing process, right?
Yeah, I think that's right. Yeah. So something I'm working on while I'm here is exactly to try to do this figure out this kind of thing and try to do this. Okay, so we looked at how quickly it goes in. Here's a time map of the temperature, I think it is. Oh no, the salt. It's the salt, I think. Salt we're showing here. So you can see the convection zone over time eat its way into the salt gradient, and eventually the whole box becomes mixed. And what I'm showing here is the difference with Prandtl number. So what we found is that at Prandtl 7, we also, in agreement with the experiment, we also formed layers. So they're very hard to see in here, actually. But hopefully, I don't know if you can see this, but there are secondary layers forming ahead of the main convection zone. And they gradually, they form, they get eaten up as the main convection zone moves in, but they keep forming ahead of the main convection zone. This happens at Prandtl 7. We didn't see this at Prandtl 0.5. So when we go to Prandtl 0.5, the secondary layers just are not forming. The convection zone goes in, and the layers don't form. Why is this? It's because, if you go back, what we found was that the main convection zone goes in much faster when you're at low Prandtl number, the blue line, compared to, say, salt water, which is the green line. So the entrainment mixing at the boundary seems to be much more efficient in the low Prandtl number run. That means the boundary penetrates much more quickly, and that leads to suppression of the secondary layer formation. Now, why is that? So how are these layers forming? Well, it seems like, oh, and here's just a picture. So here you can see Prandtl 0.5. We don't see long-lived layer structures forming. Prandtl 7, you get these very long-lived secondary layers. And you see it in the profiles too. Maybe I don't need to dwell on that right now. But how are these layers forming? Well, it seems like there's actually, Turner proposed originally that what's happening is that there's a thermal boundary layer ahead of the main convection zone that's going in. There's a thermal boundary layer there that's continuously adjusting, right, as the convection zone goes in. If that becomes convectively unstable, then I form a secondary layer. That's what's happening in the stellar evolution calculations. And it seems like that's what's happening here as well. Okay, so what we did was to look at the temperature profile ahead of the main convection zone here. And you can calculate what this moving front would look like. And it seems to be a good fit to what we actually see in the simulations. And also, if you look at the gradients, sorry, this figure is very busy. But here we're plotting height. So as you go, this is the convection zone at the top. Now we're below the convection zone, below the dotted line. And what you see is that and we're plotting gradients here. And what you see is that the density gradient, the green line, becomes negative when you form the secondary layer. So this thermal boundary layer that's ahead, the convection zone is moving in, it's thermally adjusting ahead. That thermal adjustment leads to a situation where I become unstable. To convection, I form a secondary layer. And if you use the fact that at low Prandtl number I move in more quickly, what happens is when I move in more quickly, I don't create such a large temperature contrast. The thermal boundary layer never becomes unstable. So in these experiments, what seem to be, we seem to find that the layers seem to form by the boundary layer becoming unstable. And we could also understand the Prandtl number difference based on the speed at which this convection zone is going in. Okay. And I'll just mention the other thing we looked at. So I mentioned already that in this picture, we're very sensitive to the kinetic energy flux. So if I go back, in this picture where the growth of the convection zone is based on entrainment, I have here I'm using the kinetic energy in the flow through shear instabilities to bring material across the interface and allow the convection zone to penetrate. That means we're really sensitive to whatever that convective velocity is. Yeah.
Can you just explain what else is in the equation? What's delta
Sorry.
B bar?
Yeah. So delta B bar is the buoyancy contrast across the interface between the convection zone and the stable region. And so here I'm writing down the rate of work needed to transfer material across the boundary. That rate of work is some fraction of the kinetic energy density. So it's kind of entrainment law. And then in the bracket here is just expressing the kinetic energy density in terms of the heat flux.
And are you just getting the one secondary layer in this case?
No, it's not always one. It's sometimes two, sometimes three, I think. So here's an example where we have two secondary layers, for example. It's not always one. I think well, these are a bit harder to read, the profiles. Okay, so the last thing that we looked at in this context is the effect of rotation. And this was, everything I've talked about so far there's no rotation, but in Jupiter, obviously, rotation is really important. It's rotating very rapidly compared to convective timescales, for example. So we made some estimates here, and I'll show you a simulation on the next slide. So we made some estimates here. What would rotation do? So you can go to these kind of CIA scalings, where you balance the Coriolis, inertial, and buoyancy forces for rapidly rotating convection. Right? So you see how I'm just writing down Coriolis, the inertial term, and then this is the buoyancy force in terms of a temperature contrast. And if you work through this, so we're following ONO 2020, you get these scalings where you can relate the velocity in the rotating convective system to the non-rotating velocity, and it's multiplied by Rossby number to some power. And the kinetic energy flux, if you take this velocity and then cube it, you get the kinetic energy flux. So you can also write down a relation between the kinetic energy flux in the non-rotating system and the kinetic energy flux in the rotating system. Okay, so it's just these kind of scaling arguments. And if you plug in the numbers for Jupiter, what you find is that the velocity changes by a factor of 6. So it's not that much. You reduce the velocity by a factor of 6. But for the kinetic energy density, we have to cube that. And then you go to a factor of 200. So there's a suggestion here that if you take rotation into account, this entrainment penetrative convection will be much slower because you have 200 times less kinetic energy density at the interface. So to check this, we've done one set of simulations. Now they're not very low Rossby number. The Rossby number is just below 0.1. Okay, but here's some just snapshots from these simulations. So they're Boussinesq, everything's the same. We just put in a rotation which is parallel to gravity, and now move into 3D, and then just look at the penetrative convection problem. And what you see is that you penetrate much more quickly in the non-rotating case than the rotating case. And this reduction is about what you predict from this kinetic energy argument. Okay, so the idea is that this, for Jupiter, we really need to put in rotation. The Rossby numbers are definitely small. And so maybe this is a way to delay this penetrative convection or delay mixing at the edges of layers and allow these layers to last longer. If we take the simulations at face value, what they say is that everything just mixes. It's really hard for layers to survive. So this composition profile from Juno, we're struggling to see how to make that. Maybe rotation is an answer by dramatically reducing the mixing efficiency.
This is a completely spherical simulation?
This is a Cartesian box, this one. Yeah. Rotation vertical. Yeah. Okay. Oh, and you can do some cool stuff. I see I'm running out of time now. Am I running out of time? Yeah, soon. Just to show you, you can do some fun stuff with this. So in everything I showed you, we've kept the flux held constant at the boundary to drive this penetrative convection. But in Jupiter, we know that the luminosity drops like 1 over time for Jupiter. You can just calculate the cooling of the planet. So it turns out if you take flux at the boundary goes like 1 over time, you can also get an analytic solution. And instead of just growing like t to the 1/2, it grows like the log of time. So this is another way maybe that this penetrative convection could be halted in Jupiter, because the luminosity is dropping with time. Maybe this can stop the convection zone before it gets to fully mixing the planet. So there's a nice analytic solution here. Brad Hyman and Raphael worked this out in a paper last year. So there's no Jupiter model with this fully incorporated at the moment, partially because we don't know how to handle these layers. But this is just kind of an analytic argument, just showing you. For the saltwater experiment, if you drop the flux like 1 over time, it would actually halt the convection zone at some depth, especially in the rotating system. If you put in rotation, then this is even more of an effect. So that's kind of where we are with this Jupiter problem. And I just put everything on a slide here. There's lots to do. From the simulation side, everything I showed you is Boussinesq. But in Jupiter, compressibility is a hugely important because you're mixing across many scale heights. And so just to give you a number, the kinetic energy flux compared to the total heat flux in our simulations was 10 to the minus 7 in the Boussinesq system. Very little kinetic energy compared to heat. But in the real planet, it's more like 0.1, something like that. So that just tells you you're not putting in enough scale, we're not putting in scale heights. And then we get back to, we had a bit of discussion about how exactly should we be modeling these layers in 1D and resolving them. So I think a promising avenue is probably to put in some kind of time-dependent treatment of, say, the turbulent kinetic energy density and try to feed that back in. But how exactly we do that is a completely open question. We're just really beginning to ask that. And then, what is the role of double diffusive instabilities? Because usually when we think about layering, and when people have talked about layering for planets, they usually think about the case where I put in a stabilizing composition gradient, it's doubly diffusive and stable, you break into layers. But those layers they start off very small, right? They're kind of microscopic in size, and maybe they merge over time. But here we're growing layers by driving from the boundary on a macroscopic scale using overturning convection. We're not using double diffusive instabilities. So how do I link those two things? How do we think about those two things? And I'm curious, you know, like in the oceans or in other situations, are layers forming? I mean, there are shear instabilities, double diffusive instabilities, but is there like a dynamical equivalent like this where I'm, you know, somehow forcing the system and driving layer formation like this in other situations? So that's sort of where we are with that. Okay, so if you'll bear with me, I'll just show you 5 minutes of white dwarfs. I don't know, or should I just stop? Maybe very fast. I knew I was in danger of trying to give 2 talks in one. So should I just tell you what's interesting? I just, you know, maybe one slide. Okay, and I feel like I should stop soon. Okay. So in white dwarfs, we have a freezing solid plasma forming in the center. And there's good evidence now, and this has come about from the Gaia mission, which is an astronomy satellite that's measuring distances to billions of stars in the galaxy in the last 5 years. So we have really good distances now to white dwarfs, and that means we can really tell how bright they are. So we can really tell how white dwarfs are cooling down. And so what people do is they make, just look at this right-hand plot, they make something called a luminosity function. So just a histogram of white dwarf luminosity here. So the bright ones are on the left and the faint ones are on the right. And you see there are more faint ones than bright ones. And that's because they start off hot, bright, and they cool down. But as they cool down, they cool more and more slowly. So you tend to see more of them when they're faint. But the point is that this is not a smooth distribution, there's a bump. So the red dots are the measurements. You see there's a bump here. There's a characteristic luminosity where white dwarfs seem to hang out for a while. They cool down, they hang out at this characteristic luminosity, and then they continue cooling. So how do you understand that? Well, you can understand it using the latent heat release and also the gravitational energy release from this chemical separation I talked about. And you need to put both of these in. If you put both of these in, you can build a model that more or less reproduces this characteristic feature here in the data. So this recent data on white dwarfs seems to have finally, I mean, people have been trying to do this for many years, finally shown that there's evidence for latent heat release in these objects. We're really forming a solid in the center. Yeah.
Is that an observational constraint on the right?
Yeah, these are observations here. Yeah, these red data points are from observations.
No, I mean when it cuts that up on the right.
Oh, sorry, yeah. Is this real? This is probably, I think this is selection effect cutting off. But I'd have to double check, make sure. Yeah, I think it's probably, I mean, the faint ones you don't see. So there's going to be a turnover. I think this turnover is the selection. Yeah. So we'd like to model, you know, we'd like to model this, and that's basically what we've been working on. If you release the carbon in the center of the white dwarf, you drive compositionally driven convection. And the other observational point to make is that here's a plot showing massive white dwarfs. So each dot is a white dwarf. They have different masses. And then this is the age of the white dwarf. And these lines here show when they crystallize. So if you're to the left, so a given white dwarf has a mass, over time it's going to move to the right as time evolves. And when you cross this solid line, you become solid, or you start forming solid. Over here you're liquid, over here you're solid. And the circles here show magnetized white dwarfs, which white dwarfs have a magnetic field. And the magnetic field strengths are something like 10 to 10 megagauss, you know, very, very strongly magnetized white dwarfs, even up to a billion gauss. And what you see is that the big circles tend to be to the right of the line. So there's an argument here, it's not exclusive, right? But there's an argument here that there seems to be a preference in white dwarfs for having a magnetic field once you begin crystallizing. So there's been a suggestion that the compositionally driven convection can lead to a dynamo process. Just like in the Earth's core, part of the source for the dynamo, right, is composition. Similar idea here on white dwarfs. So we've been trying to model this, and I'll just maybe finish by telling you what's interesting about this convection. I believe it's a unique regime of convection. And the reason is that there's this upgradient heat transport. So there's a potential here to really change the temperature gradient. And the reason is that if you think about a mixing length theory, when you write down the heat flux in convection, it's the velocity rho v, the flux of matter, right? And then you multiply by the superadiabaticity. So if I have convection carrying heat, it's because you have a superadiabatic temperature gradient. But we're in a situation where white dwarfs, they are really highly conductive. So they don't want to have a temperature gradient. They want to be isothermal. So if you had to guess, you'd say white dwarf would have a constant temperature everywhere. So when you look at this heat flux, you have a number here which is 0 minus the adiabatic gradient. You get a negative value. So physically what's happening is in thermal convection, you take a fluid element, it rises adiabatically, and when it gets to its new location, it's going to be hotter than the surroundings. But we're in a situation here where I'm driving the motion by composition. So now when the fluid element gets to its new location, it's colder than its surroundings. So the heat flux is actually in, not out. So I think there were discussions of this like in the 70s when people were trying to work out the state of the Earth's core. There was a core paradox, and so on, Higgins, and I forget the authors. There were discussions for the Earth's core, what exactly is happening. Is the heat flux in or out? It's a similar kind of argument, but in the Earth's core, the heat flux is definitely out, the convective heat flux. But here we have a situation where the convective heat flux is going in. So anyway. Okay, this is the part where I skip a lot of what we've been doing. We've been developing mixing line theory. We've done some simulations to really show that the heat goes in. Okay, we've really simulated this in Boussinesq simulations, the heat goes in. And we've been writing down mixing line theory. And then we've been predicting magnetic fields just using some scaling relations. I'd be happy to talk to you about. And really, I'm looking for feedback from anyone who knows about dynamos, some feedback on what we're doing here in terms of scalings. We're trying to predict what's the magnetic field that I make in these white dwarf dynamos. Okay, and again, I have a lot of questions here. So this is a much more, this is something that's really only come up in the last 2 or 3 years. And there isn't a lot of simulation work in this regime. There isn't really a consideration of dynamos in this regime. So I think there's a lot of interesting work to do here. Okay, and I think I'll stop there. I just mentioned that and stop there. Thanks. Thank you, Andy.
Very interesting talk. More questions? Louise?
So you told us a little bit about why the higher Prandtl number gave you those secondary layers. Can you just say a little bit about why the scale of those, what sets the vertical scale of those secondary layers with respect to that same argument?
Yeah, I'm not sure if I can. Yeah, that's a good question. So if I go back to the plots of the density profiles that we had. Well, so first of all, there's this simple sort of analytic scaling for the shape of this dynamic boundary layer. And we can more or less match it when you have to time average the simulation profiles, but this is the temperature profile ahead of the convection zone seems to match this kind of scaling pretty well. And the idea is that the thickness of the layer goes like the speed at which the layer is penetrating. So the faster I go in, the thermal diffusion doesn't have enough time to make much of a boundary layer, so the boundary layer is really thin. Okay, so then given this profile, you can ask, okay, where would you become unstable? And then in the simulations we measure the density gradient. And what you see is that at some point, the density gradient hits 0 over some range of height here, and you form a layer over some range of height ahead of the main convection zone. And I think that I'm really just, it's a long way to say I don't actually understand what sets that height, right? So it's something about, I think it's a really good question, and we don't have a good answer for that, I don't think. But it's of order, it's not microscopic, it's of order the depth, or some fraction of the depth, yeah. But we don't have a good theory for that, for example. But maybe there's a way to take this kind of argument and think about that. We haven't done that. That's a good question.
So convection in the ocean, if there's even the slightest lateral gradient in temperature and salinity and density, you see this evolution where you first have convection deepening the layer, and that increases the available potential energy of the system, and the next phase is baroclinic instability in the mixed layer that dramatically changes your density profile, changes the stratification. And so can that be ruled out in Jupiter? And just based on talks I heard last week, and I know that baroclinic instability is a process that could energize the jets. And so why is it being ruled out?
Yeah, it's not being ruled out here. It's just that we're just beginning to think about what rotation does in this we're really thinking here about the deep in the planets on a planetary scale. You know, what's happening to mix over that large scale. We're not looking at, for example, jet formation in the atmosphere. We're not looking at the shallow region or, you know, the winds penetrating in from the surface. We're really looking at something much deeper.
But the cooling is imposed at the top of
the cooling is, yes. Yeah, so it's,
you are going through that layer, and so that whole evolution of that surface layer could impact the evolution at depth.
Yeah, that's definitely true. And I think, yeah, for example, we've thought about the boundary flux changing with time, but we haven't thought about breaking the spherical symmetry and having the boundary cooling depend on angle, for example, which might be one effect of that, right? So yeah, no, I think it's just that we haven't got there yet. We're just really beginning to think about this. Right?
As I remember, there's a bunch of evidence from astroseismology that white dwarfs can be very strongly compositionally stratified. I was wondering whether that impacted your conclusions about the compositional convection.
That's right, yes. So there's a lot of white dwarf seismology which tends to look at the outer layers of the white dwarf. Above the carbon-oxygen core, there's helium-hydrogen layers in principle there, depending on the object. But there has been some work on looking at the carbon. Can you get at the carbon-oxygen profile? So there's no. I don't think there's any direct observational evidence showing that constrains the carbon-oxygen profile directly, because maybe there are the modes that go right, you know, into the central regions. That you
this
need.
is all fine with the fact that the outer skin can be very strongly stratified.
Oh yeah, that's fine. Actually, well, what we find, it's actually an open question. So when the core begins crystallizing, you begin growing the solid core, and there's kind of a penetrative convection problem here, where you're driving convection from the center. How far out does it go? Eventually, it'll hit the buoyancy barrier associated with these strongly stratified layers. So they're definitely important, and they are included in the models. So we have a Prandtl profile. You know, we know where these boundaries are. But ultimately, yes, this would determine kind of the maximal extent of this convection would be where you hit these strongly stratified layers. Yeah, that's right.
Right, okay. Lunchtime, I think. Let's thank Andrew again.